Hello everyone. I hope you're all healthy and well. My name is Rayan Mosli. My co-authors are Yuan, Matthew Wright, and Yin Pan. And we're all very excited to share with you our work in adversarial example crafting, which is titled They Might Not Be Giants, Crafting Black Box Adversarial Examples Using Particle Swarm Optimization. Before I begin, allow me to explain our title. My co-author, Matthew Wright, wanted you to know that he is getting old, but you all might still enjoy his taste in retro music. Our title is a reference to the They Might Be Giants band and their song Particle Man. Now let's get straight to it. The idea of adversarial machine learning attacks is to generate mass misclassifications by making small changes to the input. Lately, attacks of this kind has been extensively studied in the literature, where we can find attacks that target image classification models, like the attack we're presenting today, and also attacks in areas like malware classification, voice recognition, and even in the medical field. This is an adversarial example generated using our attack, where small changes were made to the original image, which was classified as a binder, to fool the model into classifying the image as a desktop computer. A real-world scenario of how these attacks are carried out can be seen on the slide. In this threat model, we're assuming a remotely hosted black box target that accepts inputs over the internet and returns confidence scores for each output label. In this scenario, the adversary has no knowledge of model internals and can only rely on the confidence scores returned by the model. The issue with this kind of threat model is the difficulty to distinguish between legitimate queries and malicious queries that are building up to an attack. A clear indicator of an ongoing attack is the number of queries submitted by the same source. It is thus important that attacks in this area submit as few queries as possible to avoid raising any alarms. There are two main ways to launch an attack against a black box model. The first type, known as transfer-based attacks, trains a local surrogate that approximates the target's decision boundary. The approximation is done by iteratively retraining the surrogate using specially crafted samples that are labeled using the target model. Once the substitute model is trained, it is then treated as a white box target for which the attacker has greater knowledge and access. The attack relies on the transferability of adversarial examples, where examples generated on and misclassified by the surrogate is also misclassified by the target model. This approach, however, has been shown to be less effective than the second type of attack. This second type is launched on the target directly, without requiring a local surrogate, and is done by either estimating the gradients of the target model or by utilizing certain algorithms that guide the changes until an adversarial example is generated. Both approaches rely on an iterative approach that queries the model and utilizes the output at each step to craft adversarial examples. Examples of the gradient estimation attack include zoo, nests, and bandits. Our attack is a gradient-free attack along with the parsimonious black box attack and gen attack. There are a few differences between the two types of attacks. First and foremost, it has been shown that gradient estimation attacks often achieve lower success rates than gradient-free attacks. Second, gradient estimation attacks use more hyperparameters than gradient-free attacks, which translates to an increased sensitivity and dependency on the initially chosen hyperparameter values. Tuning these hyperparameters would cost more queries for settings that require it. On the other hand, as shown in this attack and in others, gradient-free attacks have fewer hyperparameters, and they usually have predictable effects on the outcome of the attack. Finally, in comparing attacks from the two categories, it can be observed that in general, gradient-free attacks use fewer queries than gradient estimation attacks. In our attack, we use particle swarm optimization to generate adversarial examples. PSO is an optimization algorithm that iteratively improves on candidate solutions based on a specific measure of quality. Using PSO, we can disperse particles in a search space and move them until a solution is found. For each particle in the swarm, movements are determined based on the particle's best position so far, the swarm-wide best position, and previous movements made by the particle. Eventually, the initially dispersed particles converge to an optimum as best found by any of the particles. For each particle I, we calculate the velocity of the particle and add it to the particle's current position, x. This velocity has three parts: inertia, weighted with w, the exploration term, which is the difference between x and the swarm-wide best position, and the exploitation term, which is the difference between x and the particle's best position. R1 and R2 are vectors of random numbers that randomize the search process. C1 and C2, however, are used to give either exploration or exploitation more weight over the other. The most commonly used value for C1 and C2 is 2, which is what we use in our implementation. The quality of a position in the search space is determined using the fitness function. The fitness function quantifies how much a position affects the confidence of the target model towards the correct or incorrect label. For untargeted attacks, the fitness of a position is how much did the model's confidence drop in the correct label. For targeted attacks, however, the fitness is the increase in model confidence towards a specific incorrect label. Either way, the fitness function is called by every particle at every new position. The goal is to move the particles until we find the highest fitness possible. Regarding the inertia weight W, it is assigned a start value and an end value. Traditionally, W is linearly decreased from start to end according to a number of iterations. In the case of adversarial example crafting, however, we believe it makes more sense to decrease W according to the query budget allowed for the attack. We thus substitute Tmax and T in the original equation, which stands for the maximum allowed iterations and the current number of iterations, to Qmax and Q, which is the query budget and the currently used number of queries. Our attack, called AdversarialPSO, disperses the particles in the search space around the input and moves them towards better fitness. For images, particles move by changing pixel values. Depending on the dataset, that could mean 1 or 3 channels for each pixel. For color images, a pixel consists of RG and B values, each being a single channel. For grayscale images, each pixel has only a single channel. The attack begins with setting a query budget, and for our experiments, we use the same query budget as related work. Then, for each sample, we launch the attack, and if an adversarial example was generated within the query limit, it is considered a success. In addition to the number of queries, another important aspect is the quality of the adversarial image. Essentially, the less changes needed to craft adversarial examples, the better. Making large changes to the input might easily fool the model, but that would also make the attack more detectable by a human observer. To enforce a limit on the changes made to the inputs, we use the L-infinity norm, which measures the largest difference between any pixel in the source image with the corresponding pixel in the adversarial example. A simple illustration of this can be seen in the figure. The white dot in the middle of the circle represents the input, and the circle represents the furthest we can move the input according to the L-infinity limit. We use the same L-infinity as related work. A well-known problem in PSO is the velocity or particle explosion problem. This occurs when the velocity grows so much that it pushes the particles outside the allowed bounds of the search space. Even if the positions are clipped based on both the L-infinity and the natural bounds of the search space, this could still have a detrimental effect on the search process. The reason for that is velocity would eventually overwhelm the exploitation and exploration terms, and even if both lead to a location within the bounds, the velocity would overwhelm them both and place the particles at the edge of the allowed limits. The W weight is meant to fix this problem. However, it is not always sufficient. To fix this issue, we clip the velocity right before adding it to the particle position. This ensures that even if the velocity is large, the exploration and exploitation terms can overcome it and move the particles accordingly. PSO has been previously tested for adversarial example crafting, but was found to be ineffective when compared to other approaches. However, these tests were implemented using a vanilla version of PSO, which requires large swarms and many queries to run. To make PSO more efficient, we implement 4 techniques that greatly improves on the normal PSO. First, like related work, we implement a block-based approach that exploits the spatial similarity between adjacent pixels. In essence, adjacent pixels have the same effect on the model's decision. Thus, changing them together would compound the effect. We start with an initial block size, and as the attack progresses, we reduce the size of the blocks for more precise changes. Also, due to the flexible nature of PSO, we were able to minimize redundancy in changes made by the particles. In every iteration, we assign each particle a random set of blocks to explore, and for each block, depending on the number of channels in the image, a particle is assigned a single direction along one of the available channels. Furthermore, in future iterations, we make sure that the same particle does not get assigned the opposite direction of a previously assigned motion to avoid cancelling out particle movements. Once a direction along a channel in a block is assigned to a particle, it is not assigned to any other particle to reduce redundancy when exploring the search space. This can be illustrated in the bottom figure. Particle 1, which is gray, has different blocks than particle 2, which is different than particle 3. Now, although we minimize redundancy by this approach, we also allow the particles to move freely in any direction according to its velocity. So even if a block was not assigned to a particle, it can move in that direction if its velocity dictates it. Another technique we use is the reversal of negative fitness. In the parsimonious attack, the authors revert changes that have a negative impact to remove its effect on the attack. However, we took this further by not only removing the changes, but taking a step in the opposite direction. We found that for a velocity that produces negative fitness, velocity in the opposite direction produces positive fitness. Using this approach leads to finding adversarial examples quicker, which translates to fewer queries being submitted to the model. Finally, similar to related work, we start our search at the edge of the L-infinity ball and have the particles move inwards until a solution is found. This approach also helps in finding adversarial examples quicker, which also translates to fewer queries. This is the main loop for the attack process. We start with a maximum query budget, denoted as Qmax, and the set of all available blocks for this current level of granularity, denoted as B. In the beginning, the size of the blocks in B will be equal to the initial block size passed in as a hyperparameter. This main loop is terminated if either an adversarial example is created or if the attack surpasses the allowed query limit. If neither condition is met, the first step is to move the particles according to their velocity. As discussed earlier, that includes the particle's best position, the swarm's best position, and each particle's previous velocity. We then check if B contains any unassigned blocks. If yes, we assign random directions in those blocks to the particles. If not, we then perform the reversal operation, increase block size granularity, and reinitialize the particles. The reinitialization is performed to accommodate the new granularity level. Otherwise, particle best positions will still be set to the previous granularity, which would cause the particles to retract to the larger block sizes. This process is repeated until the model is successfully fooled or if the query limit is exhausted. We test this attack against nests, bandits, and the parsimonious black box attack. Nests and bandits are both gradient estimation attacks, while the parsimonious black box attack and AdversarialPSO are both gradient-free. We use the same datasets, images, and even labels in the case of untarget attacks. Our attack has two hyperparameters, the initial block size and the number of particles in the swarm. The initial block size is the only hyperparameter shared between our attack and related work. Therefore, we use the same values they used. Regarding the swarm sizes, we use between 5 and 10 particles, down from the 100 particles used in related work. Using 100 particles in the swarm would naturally be both resource-intensive and inefficient. Our implementation of PSO, however, can be more effective using fewer queries. The first thing I would like to point out is, although Nest performed very well in the targeted setting, seen in the bottom table, it performed much worse in the untargeted setting. The difference in performance between the two settings indicate inconsistency and a heightened sensitivity to the threat model. The adversarial PSO attack outperformed nests and bandits in the untargeted settings, both in terms of success rate and number of queries, and performed very closely to the state-of-the-art, which is the parsimonious attack. In the targeted setting, AdversarialPSO outperformed bandits in both metrics and only slightly trails NES in success rate while outperforming it in the number of queries. We also test the attack on a model hardened using adversarial training, which was provided by Madre Labs. In this setting, AdversarialPSO outperformed both NES and bandits and closely trails the parsimonious attack. We also test the attack on other publicly available models trained on CIFAR 10 and MNIST to test its wide applicability. The attack was consistently successful on all models and datasets. One additional feature offered by AdversarialPSO is the controllable trade-off between image quality and number of queries. Considering as the number of particles determine how many blocks each particle gets, more particles would mean fewer blocks, and as such, less changes. In other words, larger swarms mean a more granular exploration of the search space, and to illustrate this feature, we rerun the untargeted ImageNet experiment with differently sized swarms, and as you can see, the more particles in the swarm, the better the image, but the more queries used. Other than the image classification domain, we also launched AdversarialPSO in the behavioral malware detection area. For a sequence of API calls made by a malware, we use PSO to substitute APIs with functionally equivalent replacements and to select the sequence of API calls that would most lead to a misclassification. For example, the zero memory API calls can be replaced with fill memory while using 0 as an argument. Since they both do the same thing, exchanging one with the other will not affect the functionality of the malware. We're currently in the process of applying AdversarialPSO for static malware features and for Android apps. Hopefully, we'll have some results to report soon. Also, for future work, we think PSO can be used to launch a large-scale distributed attack similar to a botnet. Remote actors can work together to attack high-dimensional data, which would not be possible for any single attacker. Take an 8K image, for example. The dimensions of such an image is more than 25 times larger than ImageNet images. Such a large image can be divided among multiple actors, where each actor would focus their changes to their assigned region. Periodically, attack participants can update one another with specific changes to their respective regions so that those changes can be applied by other participants. Now, a quick recap. We use PSO to craft adversarial examples. We implement multiple modifications of the vanilla PSO implementation, which allowed us to attack black box models. We also demonstrated the trade-off provided by PSO between image quality and number of queries. And finally, discussed the uses of AdversarialPSO in other domains. Before I wrap up, my co-author Matthew Wright wants you all to know how to not be a giant, and this is how. Thank you all for tuning in. Please scan the QR code for our GitHub repo. Stay safe and cheers.